Let us start lecture 16, and the course is phase diagram in single component and binary systems. And today's topic will be phase equilibrium single component system, and we are going to take H2O, and later on we will also consider one more system which is CO2. If you see last class, we have seen that free energy of liquid water is equal to free energy of solid water when it achieves equilibrium at a temperature 0 degree Celsius and 1 atmosphere pressure. And if we keep the pressure constant and reduce the temperature, we will see ice will form spontaneously, and whereas if we increase the temperature, ice will melt and then it goes to liquid. That is what we have seen. So, today what we will plan to do is basically we try to see that if we change the pressure and temperature both, how the equilibrium between solid and liquid would vary, okay? And that will actually demarcate between the solid zone and the liquid zone. So, as we see that the generic equation what we see is the Gibbs-Duhem equation V dP minus S dt plus mu I dNi. Now, it is a closed system, fixed composition. Why fixed composition? Since it is single component, okay. So, that case I can ignore this because it does not matter, it will be always fixed, that composition term will always be fixed, there will be no contribution from the chemical potential. So, I can write this as V dP minus S dt. We have seen before also. So, this not to be considered. Okay. So, once we write this, so then I can see that if I try to see what happens to this at a constant pressure equal to minus S. And if I do it again, equal to minus ds dt constant pressure, it should be equal to minus Cp by T. Why? Because ds equal to Cp dt by T. So, from here it comes. So, and entropy cannot be negative. So, this is a positive quantity all the time. So, entropy is a positive quantity. But entropy difference which is S, del S can be negative quantity depending on change. So, let us say a liquid to solid transformation, then this change can be negative, because liquid entropy is higher than the solid entropy. Okay. We can also write this as I can write this, and let us say here I am changing from solid to liquid. So, this means here also solid to liquid. So, when I am taking solid to liquid, the SL is greater than SS. So, then del S solid to liquid should be greater than 0. So, it is a positive quantity. So, that means if I try to see a slope for this delta G divided by delta G and T, then that slope would be having a negative slope. Similarly, G versus T would also have a negative slope, fine. So, now let us see how that slope varies. Let me take first a solid phase. okay, solid water phase, and we are changing temperature at a constant pressure at pressure equal to let us say 1 atmosphere. Okay. So, how the change would vary? So, this is G as a function of T, and for solid also this equation, this would be minus S of S. So, it will have a slope like this. Okay. This is G of solid, and the slope is minus S S, which is this. Similarly, if I try to look at liquid phase, at temperature with temperature T at pressure equal to 1 atmosphere. So, the temperature is a variable. So, then delta G, this is for solid, delta G delta T constant pressure liquid should be equal to minus SL, and SL has a higher value than SS. So, it will have a slope like this. Okay. So, this is SL, this is S, I can write here. SL, which is this. And now, if I look at this point, since it is 1 atmosphere, we will see that this point appears at 0 degree Celsius. Okay. So, this temperature is varying this way and G is varying. So, this is the variation. Now, if I try to look at T with delta G, now let us see, it is basically solid to liquid. So, that means delta G solid to liquid constant pressure should be equal to minus del S solid to liquid. This particular term is a positive quantity. So, since it is a minus, that slope would also be negative. So, that slope would be like this, and interestingly this 0 Kelvin, 0 degree Celsius, not Kelvin, 0 degree Celsius, 1 atmosphere pressure, this particular value, cross section value, what would be that? This value would be 0. So, it is starting from 0. So, here it will go up, here it will go down, because I am considering only solid to liquid. Below 0 degree Celsius, I see solid phase to be stable, beyond 0 degree liquid phase. So, that means solid to liquid happens beyond 0 degree, and below 0 degree liquid to solid phase happens, and since liquid, so that means liquid has a higher free energy, and here I am taking solid to liquid. So, that free energy change should be positive. So, liquid solid to liquid is not a spontaneous process below 0 degree Celsius, but liquid to solid to liquid beyond 0 degree should be a spontaneous process. Fine. So, here why it is at this place, solid to liquid non spontaneous, since greater than 0, and here we have solid to liquid spontaneous, since delta G solid to liquid less than 0. Okay. So, that is what we have understood. This is the kind of phase transformation we will have at 0 degree. So, now if I try to look at plot between pressure and temperature, if I fix it at 1 atmosphere, so this is 1 atmosphere pressure, and if we fix it this particular to be 0 degree Celsius, so then I will get a coordinate point 0 degree Celsius 1 atmosphere pressure. So, that time these point indicates in that particular plane, pressure temperature plane, as the equilibrium point, where solid and liquid both will coexist. Okay. Now, if I keep the pressure constant below this point solid, beyond this point liquid would be stable, because that value, free energy value of liquid is lower than here, GL less than GS, and here GS is less than GL. Okay. That is what we have seen, and this is, please take this point, this is G liquid, okay, free energy of liquid. And remember, this is all molar free energy, we are talking about 1 mole of liquid and solid. So, it is all about 1 mole of liquid and solid, both the cases we are taking 1 mole. Okay. So, that is what these are all molar free energy. Okay. Now, if I try to change pressure, let us say I change the pressure this way, and if I change the temperature this way or this way, what would happen to this point? Which way it will move? In order to see that, we have to bring in one more factor, which is basically, since we have seen dg equal to v dp minus s dt. So, these equation we have to bring in. Let us say if I take for solid, so then it would be delta G solid equal to V solid dP minus S solid dt. For liquid, and we are taking that it is a transformation from solid to liquid. So, that means liquid is the final state and this is the initial state. So, that is what we are taking. So, then from this I can take delta G L equal to delta G S. Let us say it is at 0 degree Celsius and 1 atmosphere pressure, fine. So, that means it is under equilibrium, no? Equilibrium. So, I can write it as Vs dP minus Ss dt equal to Vl dP minus Sl dt. Since it is solid to liquid, I convert everything into solid to in the form of solid to liquid. So, I can write Vl dP minus Vs dP equal to Sl dt minus Ss dt. So, that gives me Vl minus Vs dP equal to Sl minus Ss dt. I can write dP dt equal to Sl minus Ss Vl minus Vs. Since we are taking 1 mole, so this Vs as well as Vl are basically molar volume of solid as well as liquid, fine. So, that means del V m solid to liquid should be equal to Vl minus Vs. Applying similar logic, I can write Sl minus Ss should be equal to del S solid to liquid. Okay. So, this gives me del S solid to liquid, del Vm solid to liquid, and Vm is basically, this indicates molar volume, 1 mole substance. So, this one also, because it is a 0 degree Celsius, which is the thermodynamic melting point and 1 atmosphere pressure. So, I can actually write it as delta Sm, which is solid to liquid entropy of melting. So, we will analyze this part, how to calculate entropy change at different temperatures other than melting point. In fact, melting point one can actually calculate this delta Sm solid to liquid. Now, then I can write this one as delta Sm by delta Vm. Here m means melting, okay, and here m means I can let me put it as this is basically molar volume. Okay. So, final equation, if we try to write it in this fashion for the solid and liquid water, divided by delta Vm, and now I can get an equation with respect to enthalpy of melting. And enthalpy of melting can be found out by a DSC method, which is called differential scanning calorimetry. If we perform that, we can actually calculate that value, and that value is basically first order function. Okay. So, now delta Sm equal to delta Hm divided by Tm. Tm is the melting point. And this is so this can be calculated using DSC, differential scanning calorimetry. Okay. So, the melting point. So, I can write this as dP dt delta Hm by Tm delta Vm. Okay. More generic form, let us say it is not about melting, let us say some transformation, solid to solid transformation also, like gamma iron transforming to alpha iron. So, that means FCC iron converts to BCC iron. That process also there will be a transformation temperature. That transformation temperature and there would be associated heat of transformation. So, in order to have a kind of similarity of other transformation character, similar type of transformation, I can write a generic equation. So, the generic equation would be dP dt equal to delta H, I would say trans delta V transformation. Okay. So, this is a generic equation. So, this equation is called Clapeyron equation. Okay. Fine. This is called Clapeyron equation. Now, what is the importance of that with reference to the diagram what we showed here? So, this diagram. So, in fact, this diagram, any point, this is a point on pressure temperature plane, and on that plane what would be dP dt, if that we measure, then we can definitely mark, if we change the pressure and temperature, what would be the position of that equilibrium point. Okay. So, now in order to understand that, let me just check this. So, let me come back to this dP with reference to 1 mole of water. Okay. So, there this would be equal to delta H m T m delta V m, and here I am talking about solid to liquid transformation. Let us understand what is the value of liquid H solid V m solid. In fact, this is greater than Hs, this is smaller than Vms. This is a kind of anomaly in case of water, where solid has a higher molar volume than the liquid. Okay. So, now you see delta Hm is nothing but HL minus Hs considering solid to liquid, and this is at Tm, okay, which is 0 degree Celsius, right, in case of water. So, this should be positive, greater than 0. Now, here Vm liquid, which is the final stage, Vm solid, which is the initial stage, because we are considering solid to liquid, which is nothing but delta Vm solid to liquid, should be less than 0. Okay. So, that means it is negative. So, then this slope becomes, Tm is a melting point and this Tm is in Kelvin scale, remember. So, this is in Kelvin scale. Okay. So, we will, if time permits, we will talk about why it is to be taken as Kelvin scale. So, dt should be, okay, this slope becomes negative. Okay. So, once it becomes negative, that means if I go back to that plot P T, and we saw that at 1 atmosphere pressure and 0 degree Celsius, I have this particular location where solid and liquid both are at equilibrium. Now, at that point, if I try to draw this dp dt, the slope would be a negative slope passing through this. So, this is dp dt equal to negative. Okay. So, this negative slope we are getting. So, that means if we increase the pressure, what does it mean? If we increase the pressure, the melting point would go down, and if we decrease the pressure, the melting point would increase. So, this is pressure, let us say this is increase, this is increase. So, that means pressure increases, should decrease, pressure decreases, should increase. This is a great finding. In fact, on that basis we can have many examples. Okay. One such example is when we see that how if you take two ice let us say ball or ice cube, you take them in your hand and press it hard and then release it. You will see that two ice cubes will be joined together. Okay. So, that particular joining part can be explained through this consideration. So, that means when that happens, when what you are doing, you are increasing the pressure, and that is what the melting point drops. The local liquid, locally there will be liquid formation, but once you release that pressure, then the melting point increases, but that particular thing was in liquid. So, they will try to solidify again. Okay. So, that is what the two things are joined together. Okay. So, we will talk about these particular examples in a greater detail in our next lecture. So, till then at least one thing you understand, by doing this analysis we are actually demarcating two regions. One region is solid another region is liquid. Okay. The right side of this line is liquid, left side of this line is solid. Okay. So, now you are actually making a demarcation between solid zone and liquid zone, and any point on this line, where solid and liquid both will be under equilibrium. Okay. And if we switch from that point, keeping the pressure constant, either you will get liquid or solid depending on which side you are going. If you are going right side of the line, you will get liquid. If you are going left side of the line, you will get solid. So, let me stop here. So, we will continue our discussion on single component phase equilibria, and we will try to see phase equilibria between solid and vapor as well as solid and liquid and vapor, and then you will see this particular phase diagram will be complete. Okay. And while doing that, we will try to calculate some of the values and see whether it is matching or not. Thank you very much.